Okay, so we'll briefly revise this JK flip-flop one more time. So, as we have already introduced the concept of an SR latch or RS latch, and we already saw that there were these three states that are valid, which is S and R are both equal to 1, which holds for the memory state, which is going to retain the contents, retain the contents. After that, we also saw that depending on the value of S and R, if S equal to 0, R equal to 1, that can reset the circuit. If R equal to 0, S equal to 1, that is 0. So these are the two states that were possible, but we saw that 0 and 0 was not possible, in the sense that this is going to be raising some kind of a metastable condition, so as zeros and ones could get into an undeterministic oscillating stage, right? And the final output cannot be determined, and it depends on, so like the fractional amount of nanoseconds, maybe one NAND gate is faster than the other NAND gate. Based on that, the results is going to settle down. Okay, so we saw one solution using the D latch, where we were instead of supplying the uh, S and R independently, we were forcing that S and R are complements of each other, and that was achieved by using a NOT gate here. So if you look at the this portion of the slide, there is a NOT gate here. So you can think as if this is again an SR latch, but this is with a condition that S is equal to a complement of R or vice versa, right? And if you make write enable is equal to 0, if you make write enable is equal to 0, in that case both S and R is going to be 1. In that case, this is going to be a memory hold situation, right? Memory hold state or configuration. Okay. Whereas if you put write enable is equal to 1, if you put write enable is equal to 1, in that case it is going to purely depend on the values of R and S. Okay. Or on the top we are using S as the notation, so we'll put it S because this one is reflected as S, this one is R. This will be S bar because there is a NAND, this is a NAND gate, right? So if you have S here, this is going to be S bar. If you have R here, this is going to be R bar. So that's what the nomenclature is a little bit confusing here. Sometimes we call it SR, RS, or sometimes we have inputs as S bar or R bar. So the concept is generally the same. You need to understand that if both of the inputs in this particular part of the circuit are 0 and 0, that is disallowed. But if you have both of them as 1 and 0 and 0 and 1, it is going to set or reset Q accordingly. This is the thing that you need to know. Rest of the things you can work out depending on what kind of circuit is given to you, you can work out. Okay, and the solution to that, as you now saw, was the D latch, and D latch had one problem. This was level triggered, that's why it is called a latch. And we also saw a solution with two D latches successively joined with each other, with one with a positive clock and other one with a clock negated, right? So that was going to give rise to an edge triggered solution, which is basically called a D flip flop. Okay, so now that was a solution from D latch to a D flip flop, but D flip flop only had, or D latch only had one input. That input was the D value that you are trying to put to be reflected on Q, right? What happened is there is one more extra circuit. That circuit was trying to have the lost input that we had in case of SR, because SR you had two inputs, just that one input was not valid or forbidden. That was lost in case of D latch or D flip flop because on only one input. So this is the only input that could have been given here. It's the only input. Okay, so this is known as a JK flip flop, named after his inventor Jack Kilby, who also made integrated circuits for the first time and won a Nobel Prize in physics in early 2000s, or I think probably in 2000. So this is the JK flip-flop. The extra thing that the JK flip-flop has is the feedback from this Q bar channel, right, to the input. Okay, and note that here it is not D and D bar, which was the case in case of this thing, right? You had D here and D bar was the other input. In this case, you have J and K to be two independent inputs. Okay, so this is one input which is J, the other input is K. One input is the clock, which is very similar to your write enable. Okay, that is the same as D, right? The extra thing is that we have the top, in the top NAND gate where we provide J, we have an input from Q bar. This is an extra thing. Okay. So this is the feedback. The other thing that we have is from Q. So this is something that you need to remember, or this is going to have implications in the state table of the flip-flop. So if you see from Q, there is a feedback that is going to the lower NAND gate where K is being supplied, and from Q bar there is a feedback to the top NAND gate where J is being supplied. Okay, so this is called a JK flip-flop, and the JK flip-flop has the following kinds of states. One is J equal to 0 and K equal to 0, which is nothing but a memory hold state. I think we worked out an example like this in the last class. We can just verify. If you have J equal to 0 and K equal to 0, one input can make sure that the output of these AND gates are going to be 0. So doing an inversion because of a NAND is going to result in 1 and 1, and then it becomes a same configuration as an SR latch and it goes to a memory hold state. Okay, so this becomes a memory hold state. The next one was J equal to 0, K equal to 1. So in that case also we can figure out that J is going to, the Q is going to be set to 0. This is again it is encouraged that you work out. We have already showed this kind of an example in the previous lecture. So clock is equal to 1 is something that you need to assume. You can take any value of Q, right? Q could be 0, Q could be 1, or Q could be treated even as a variable. Okay, so in that case here what you are getting is Q bar, and what you are getting here is Q, right? So Q bar dot 1 is basically Q, right? Q bar, and you take a not of that, which is basically the output of the NAND gate. So Q bar dot 1 NAND of that is basically going to result in Q. So I'll use the capital letter. Okay, so this basically becomes Q. Okay, and you can work out the rest of the things, that what exactly is going on in the rest of the circuit. You have to you can see that what is the value that is coming. Okay, so this was, I think, discussed in details for the entire circuit. You can try out with Q equal to 0 as well as Q equal to 1, and we will soon see the state diagram. That is just to recall how the state diagram looked like. Similarly, here the output is going to be determined based on the values of J equal to 1 is an input and K equal to 0 is an input. Clock is high. Here you have Q, and here you have Q bar, right? I think this is a small, again, a mistake that has been done. Let me quickly, where is this? Okay. Okay, so this is Q, this is Q bar, this is Q bar, and this is Q bar. Okay, so this is now going to be Q bar, and this is Q. Q dot Q bar is going to be 0, so this is going to become 1. Okay, and you can actually see that q is going to be written as 0, because if j is equal to 0, q is going to become 0. Okay, so same thing in the next case also. You can try it out and you will see that q is going to be 1 and q bar is going to be 0. So this is just the opposite one. If you use j equal to 0, k equal to 1, you clear this value of q to 0, you set the value of q to 0. If you make j equal to 1 and k equal to 0, you set the value of q equal to 1. Okay, so these are the different states of the JK flip-flop. It could either be in a q equal to 0 state or q equal to 1 state, and based on the value of q, we call the circuit is set or reset. And if we want to hold the memory, right, if it is in a set state or reset state, doesn't matter, as long as j equal to 0 and k equal to 0, as we have studied earlier, j is equal to 0 comma k equal to 0, this is always going to hold whatever is there in the memory. So if it is a set state, it is going to remain in the set state. If it is in the reset state, it is going to remain in the reset state. So that is basically going to be the output for jk equal to 0 and 0. J equal to 1 and k equal to 0 is going to set the circuit. So that is already assumed that it is in the set state. That means that q equal to 1 and q bar equal to 0. If you put again j equal to 1 and k equal to 0, it is going to be the set state only. It is not going to go to anywhere. Same thing, right? Similarly, if it is in the reset state and you try to put j equal to 0 again and k equal to 1, that is going to be in the reset state anyway. Okay, so doesn't matter, right? And if you want to reset a set circuit, for example, if q is equal to let's say here q is equal to 1, let's say here q will be equal to 0, and if you want to make q is equal to 0 from the q equal to 1 state, that is you are trying to reset a set circuit. In that case, you have to put a j equal to 0 and k equal to 1. So it's very simple. J equal to 0 and k equal to 1 is always going to reset the circuit. Doesn't matter if it was already reset, it is going to be staying in the same condition. If it was in a set condition, it is going to move in a reset condition, and vice versa. So if it was reset, if you just alter the conditions, put j equal to 1 and k equal to 0, then you get q equal to 1. Okay, so this was sort of trivial, kind of revise this, but this is very important for future designs of circuits using such JK flip-flops. Okay, so now we have one more condition that is left, where j and k are both 1. So we have already studied that if j equal to 0 and k equal to 0, this is going to lead to a memory hold state, right? We have studied a set using let's say j equal to, we are putting j equal to 1, k equal to 0 to set the value of q, and j equal to 0 to reset the value of q. Here both of them are 1. Okay, so we can try seeing what happens if both of them are equal to 1. So j again is equal to 1, clock is equal to 1, and k is equal to 1, right? And what is the value of q? You can take some value of q. Let's say the value of q is 0. Okay, and then the q bar is going to be 1. Okay, so if q bar is 1, this value is going to be q bar, so that is equal to 1, and if q equal to 0, this is going to be 0. Okay, so now if you see 1 1 1 on the top, if you AND them, it's going to be 1, right? And not of that is going to give rise to a 0. Okay, and on the bottom part, this is going to be 0 and 1 and 1. So 0 and 1 and 1, if you AND them, it becomes 0, but you are doing an AND operation, so this is going to become 1, right? So I'll write it in a different color because this happened after this thing. There's a concept of time. So this is 0 happened, then 1 happened, right? After that, what will happen is that 0 is being supplied to the NAND gate on top, right? So definitely the output is going to be 1. Okay, so this output, this 0 goes inside, right? And this is an AND gate, so that output is definitely going to be 1, right? So this 0, you can see this is going to change back to 1. Okay, and this 1 can come here, 1 and 1, the output is going to be 1. If for an AND gate, the output is going to be 0. So as you can see, this 1 is going to be switched to 0. Okay, so once this is changed one more time, as you can see, the values might change again because there is a feedback. We will come to the discussion later. But as you can see, after completion of this one cycle from this JK inputs to the what we call is the first layer of NAND gates. So this is a first layer of NAND gate. Then there is a second layer of NAND gate with the feedback. Okay, and the value actually changes from 0 to 1 and the Q bar changes from 1 to 0. You can try out a similar example where the value initially could be Q equal to 1 and Q bar equal to 0. In that case also you can verify that 1 is going to be changed to 0 and 0 is going to be changed to 1. So this is just going to flip the output. Whatever be the value of Q, if it is 0 or 1 doesn't matter, Q becomes Q bar and Q bar becomes Q. So this is often called a toggling state. Toggling means it inverts its value. Okay. So J equal to 1 and K equal to 1 is going to give rise to a toggling condition. In the previous three things, there was no toggle. There was either setting, resetting, or this is going to hold the memory element. Similarly, in case of D also, if you enable this write enable is there. If you put D equal to 0, the value is going to be Q is going to be 0. If you put D equal to 1, Q is equal to 1. There is no mechanism in the flip-flop itself to toggle its states. For example, in a D flip-flop, I cannot do like if it was 0, I want to make it 1, or like some kind of value inversion is not possible, right? But in case of JK, it gives you an additional advantage that if you put J equal to 1 and K equal to 1, internally whatever be the value of Q, this is going to gets complemented. If it was Q, it will become Q bar. That is not there in D. D has to be deterministically written. If you put D equal to 1, whatever it will be copied, 1 will be copied irrespective of what you had earlier. If D equal to 0, Q is going to be 0 irrespective of what was there earlier. Okay, so this toggling gives you a very nice feature which is used for many interesting designs, for example counters and so on. So this is called a toggle. Okay, so if it is Q is equal to 1, this is going to be switched to 0. If it is 0, it is going to be switched to 1. Okay, same demonstration we kind of already covered. So this is the same state diagram, and in that state diagram we are going to add one more or two more additional edges. One is from set to reset. So if it was set and you put JK equal to 1, it is going to be reset and vice versa, right? So this completes the various states that are possible in case of a JK flip-flop. Okay, so now let us look a little bit deeper into this problem of toggle, right? So just a summary, I'll come to the toggle part just after this slide. So this is called the JK truth table, where you have the different inputs and the corresponding outputs for Q, right? Very similarly, you can do the same thing for D, but D is very simple because there are only two inputs that are possible, D equal to 0 and D equal to 1, whereas in this case there are two inputs JK, considering clock is always high because there is no point in studying in this particular context where clock is not present or the clock is not triggered. So these are only studying the situations when the clock is triggering from a low to high state, right? So this was studied earlier, this was also studied earlier, and we studied this now. J equal to 1 and k equal to 1, the outputs are going to be accordingly, right? It is written, and q and q bar are complements of each other. So this is something that you need to remember. Okay. So now, as I told you, let us look into the case of toggling one more time. Okay. So here we just now studied that once j and k inputs are provided to the system, you pass through the first layer of NAND gates. I can call them as the first layer. Then there is a second layer, and then you get an output. But remember that this is not the end of the story, right? Once you get a toggled output, these toggled outputs are also fed back to the circuit, right? So if you see, once this becomes let's say 1, right, 1 is fed back here and so on, but this value, right, let's say this value of q bar, which was originally 1, now set to 0, is also going to be fed back to the input, right? So let us follow only this line, this green line that I am drawing, which was originally 1, right? Q bar was originally 1, but now because of this value change, this is again going to be rewritten. So now this is no longer 1, this is going to be 0 now. Okay. So in case of this other input, which is q, the value of q is no longer 0, it has become 1. Okay. So if you follow this particular line, this value which was originally 0 has now become 1. So this will become 1 now, right? And after that, what will happen? The same phenomenon is going to continue. This is again, as you can see there, just the roles have been reversed. So on top, if it is 1 1 1 and bottom it was 1 1 0. Now in the bottom we have 1 1 1, on the top we have 1 1 0. Again the same phenomenon is going to take place. Okay, just in a reverse way. So again there will be a toggle, right? So how long this is going to toggle? Nobody knows, right? It basically depends on, as long as we have clock equal to high, right? If the clock is high, then it is going to keep on repeating this, right? And one more thing is, as you can see that let us say this equal in the previous cycle, this was 0, right, and this is 1, right? And it may happen that the input to this particular NAND gate was anyway 0 earlier, right? It was not 1, right? Originally q was 0. Originally this was originally 0, right? Because of this particular NAND gate, this has become 1, right? And then only this 1.1 is 1 and the not is 0, that is why it is 0. So it is inherently dependent on whether you are actually looking at the original value 0 or the value that has been computed by this top NAND gate, right? So let us call it as the NAND gate A, this is NAND gate B. There is a question of whether this computation by the NAND gate A or the output of the NAND gate A happened earlier compared to the output of the NAND gate B. It may happen, right? Or if NAND gate B is faster, in that case the original output will be considered, right? Instead of 1, we will consider 0, right? And this was originally 1, right? So in that case, instead of 0, we will consider 1. So things may change, right? There is a little bit of uncertainty here, and this uncertainty is dependent on the speed of the individual NAND gates A and B. We do not know. I showed you a condition where A wins and B doesn't win, and accordingly it toggles. But it may happen the other way around also. B wins, or whoever wins in which cycle is not deterministic. Okay. So as long as the clock is high, right? As long as long as the clock is high, there is a continuous feedback that cycles through the circuit and it toggles, right. So if I make the clock high, there is a toggling, for sure there is a toggle, but again there is a toggle, again there is a toggle. How many times we do not know. As long as the clock is high, it is going to toggle. So that is actually called in literature race condition. Okay, so we have a picture here that we don't know whether Q wins or Q bar wins, because whenever the clock goes from this low to high state, there is a positive trigger, for example, we do not have one toggle, but there is a number of toggles, right. There is a number of toggle, and if you have even number of toggles, then it is not going to end up in a so if you have one toggle, then if it is 0, this is going to get to 1, or odd number of toggles. Okay, but if you have even number of toggles, then it is going to be in the same state. If it was 0, it will be in 0. If it is 1, it would be 1, right. So the toggling won't actually effectively manifest itself, right. It will of course toggle, but it will toggle some uncontrolled number of times. You will not get the effect. Okay, so what is the solution? The solution to this is, as you can now kind of understand, is this is responsible. Why is the toggling taking place? Because of this clock is kept high for a higher period of time, longer. If the clock was kept high for a very, very short period of time, then this thing would not have happened, right. Because one time the value gets to the this thing, clock would become low, and this is not going to continue anymore. Similarly for Q, whenever this feedback is computed and goes here, maybe the clock is low. Okay, so it cannot enter the circuit anymore. That is not going to create another toggle. Okay, so as long as the clock is high, this is going to keep on toggling. So this is basically because it is almost behaving like a latch, is actually becoming like a latch. So as long as the level is high in the clock, the NAND gates are going to toggle, and the timing pulse, as you can see, the timing pulse must be very short, because a change in Q before the clock pulse goes off can drive the circuit into an oscillation, which we call racing. So the clock pulse is high, the circuit toggles. When the output of Q or Q bar comes back as a feedback, it finds the clock is still high, then it will again toggle, and it will continue for an uncontrolled period of time, right. So the only solution here, without making any changes to this circuit, is to make the clock pulse as narrow as possible. Okay, but in a real life situation, in considering all sorts of manufacturing defects and so on, it is very difficult to make a clock pulse very, very narrow, which is comparable to the latency of the NAND gates, right. So basically it depends on how much time it takes for the signal to cross these two layers, right. So this is your time, and your pulse width, right, the width of the clock has to be even shorter than that, right. So the next time it is not successful in coming back. Okay, but that is not a reality which is possible, because these gates are very, 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 very fast, right, and this is also not very deterministic, right. So the bit that you get at the end of the day, the computation that you do at the end of the day, that has to be deterministic. It cannot depend on the race condition, or it cannot depend on which NAND gate was faster than which NAND gate, right. So we will get answers that cannot be strictly determined. Okay, so this solution with j equal to 1 and k equal to 1 is not favored, because this is going to give rise to a race condition. Okay, for the rest of the things it is fine. You can set, you can reset, and you can hold the memory. But once you go into if you want a state that requires a toggling, then you have to modify the circuit, and the modification of the circuit is exactly the same modification that we did in case of a D latch to a D flip flop.